Hello, students. We are into section 3.4. So the problems do look pretty similar between A and B, as you know. I think I've got most of the same questions here. Let's take a quick look. So 1 through 9, 11, 16 through 19, 20, 20. Okay. So yeah, the first few problems, but again, you're kind of just looking at demonstrating how multiplication works in the different arrays or different models, the repeated addition, the rectangular array, the area model, and the Cartesian product. So again, taking an example and showing how this works is going to be good. And if you haven't, again, you can flip back in the pages of the book. You can watch my other very short video over 3.4 that kind of goes through each of these different components that were in the textbook. And then as you're looking through, here's a Cartesian product one, but then what multiplication is suggested by the following model. So understanding what is the actual multiplication problem from these, filling in the blanks, right? You are finding a whole number. Now remember, whole numbers have to be in that. When we say whole number, it's that 0, 1, 2, 3, 4, and so on. Negative numbers are out. So when you look at this, it doesn't mean that there will always be a, see if bigger. So here, 3 times something gives me 15. This again is the foundation of algebra. So when we start thinking about algebraic thinking, you might as well write 3 times x equals 15 because it is. It's the same concept that we had before. Sporting goods store has this many and this many, this many. Nuclear interior of car. Ooh, here's some closure ones. So again, for these closure ones, you want to be thinking, are they closed under multiplication? And so if I multiply these two numbers, do I get something that is in the set? So now this is part A, but if I was doing this problem, I would be looking at this. Let's just say I think I did 0, 1 in the other one, so I'm not going to worry about it here. Here, these are even numbers, right? So 2, 4, 6, 8, 10, 12, and so forth. So if I multiply two even numbers, right, will I get another even number? So let's just do like 6 times 8. Well, I can see each one of these numbers is an even number. And so when I multiply those, I get 48, which is an even number that is in the set. Is there any way for me to get even number to multiply and get an odd number? And the answer is no. So if you need to, you could write an even number as 2 times a, because this is 2 times some number. It's any even number is a multiple of 2, and 2 times b. So when you multiply them together, you will always end up with 2 times something. And in this case, it would be 2 times a times b. So again, you're ending with an even. You're starting with two evens. You're going to end up with an even at the end of the day. And lastly, this one's kind of an interesting one, 147. So if you're unclear, because it looks like this sequence is going to be things that look like 3n, plus 1? Right? If I put in a 0 here as a whole number, I get 3. Then I just keep adding 3, 3, 3. So if I multiply that by another number that kind of looks like this, I wonder if I'm going to end up with a 3 times something plus 1. So let's take a look. Now, again, could you do some exploration first? And I would say yes, absolutely. So if you did a little bit of exploration, you could try some numbers, right? What is well, 1 times 4, 1 times anything is going to be in the set, so don't worry about that. So 4 times 7, right? 4 times 7 is 28. Okay. Well, let's just keep counting up. If we kept counting up, we add 3, 3, so 13, then 16, then 19. 22, 25, 28. So I'd say, okay, 28 is in the set. Next up, 4 times 4. Well, 4 times 4 is 16, and that's in the set. So what we notice is we start to see, okay, well, wait a minute, that's interesting. It looks like at least the first few we tried are in the set. And what we do to kind of determine whether it is or not is we generalize. So take a general form of any number in the set, multiply it by the general form of a different number. So notice I'm choosing different variables here because they don't have to be the same number. And when I multiply that out, I get 3n times 3m, right? This is the distributive property, plus 3n plus 3m plus 1. So if you take a look up here at the beginning, I end up with, I could factor a 3 out of each of these and be left with 3nm plus n plus m plus 1, and I end up with 3 times some number plus 1. So this is 3 times some integer plus 1. That means it is closed under multiplication. So when I multiply them, I will get something of the same form. Without something like what I just showed, without that, all you've done is shown a bunch of cases that work. Cases that work is not enough. Okay. Question 8's a good one. You'll see something along these lines as we keep going on. If I take the whole numbers and I take out the number 5, is it closed with respect to addition? If I take the set of whole numbers, take out the number 5, is it closed with respect to multiplication? So be thinking about this. Okay, how can I make the number 5 using addition, right? So 5, you say, oh, well, that's 1 plus 4. Is 1 and 4, are those both in the set of whole numbers? And they are. So they would be in the remaining set. So 1 plus 4, in order to be closed with this brand new set, 1 plus 4 would have to be in there as well. So this would definitely be a no, and you could provide a counterexample. But when it comes to multiplication, right? What would I multiply to get to the number 5? And if I pulled the number 5 out, does this fail? Is there a way that I can multiply, get to the number 5? And anyway, that's the questions being asked. Rename these using the distributive property. Okay, use the distributive property. Which of these properties? So again, knowing the properties. I think, you know what? Let me flag one of these down because I think this is probably one of the most common mistakes in the course. Something like question B. And the reason is it looks similar to question A. And some students, when they write their notes down, they will write down associative property includes parentheses. Remember, the idea about the associative property is like in part A, where I changed the grouping. So notice 5 times 4 was being multiplied. If I change the grouping, 6 times 5 is being multiplied. Okay. But take a look. This is where I want you to take a look right here. Take a look in part B. Is the grouping changed? The first one on the left-hand side says 5 times 4. On the right-hand side, it says 5 times 4, which is now 4 times 5. So the grouping never changed. It's still a 4 and a 5. What changed was the order. And since the order changed, that is the commutative, not communitive, like communion at church. It's not like that. It's commutative, like a commute forwards and backwards from work. All we're doing is changing the order. Commutative of, oops, a glitch with the pen there. Sorry about that. Commutative of multiplication. Okay. So keep that in mind. That is a tough one. And the same is true for addition. So again, if I have 3 numbers and I'm adding them all together, if I don't change the grouping, I just change the order, it's not associative, even though there are parentheses. Parentheses are not the key piece. Now let's see here. Product can be split things up. Oh, I like that. Okay, what properties are being used? Use this technique to do 32 times 12. Oh, that is actually kind of a fun one, right? 32 times 12. Break the 32 up. Make your life easier. Let's see here. Grab some white space. And here we go. So they say do 32 times 12. You're going to try to do this mentally. Okay, so if you can do it on paper, that's great, but you just want to write down what your thought process was. The goal is that you do it in your head. So I would write down 32 times 12. I would write 30 plus 2 times 12. And the reason is that the 30 times 12 is like 3 times 12, and 3 times 12 is not bad. That's 36, but with the extra 0 on here, we know multiplying by 10s gives me another 0. And then 2 times 12 is just 24. So at the end of the day, I get 384. So that's how I can kind of mentally do it. I don't have to have this all written out. I'm only writing down my thought process to get there. Okay. The distributive property over subtraction is actually a really nice one as well. If your number is like the 32, see how 32 is just a little bit above 30? Make it 30 plus something. But I would do almost the same thing if I was doing, let me go back to this one. Let me go back to this one. Because what if I was doing not 32 times 12? What if I was doing 29 times 12? This one's a little bit more challenging for most people. because they look and they think I have to do 20 times 12 and 9 times 12. But you don't. Think about 29. How could I decompose it? It's probably easier to think about it as 30 minus 1 because then the 12 times 30 still gives you the 360, right? And then you can say, and now I'm taking away 12. And by the way, when you're taking away 12, think about taking away the 10 first, because again, that's going to be kind of easy. And then when you're done, take away the 2. So I would take away the 10 and then take away the 2. So I don't have to think about the regroupings and all of those pieces. It's going to make it a little bit easier for me. Okay, and that gives me 348. So again, think about this. The goal of this is that you become, quite a bit more familiar. You can do things that maybe you thought you couldn't have done before. Let's see here. Show that this works with the distributive property with an area model. Here they're going to show an area model right here to demonstrate that, what do we got here? Explain why a squared minus a plus b quantity squared minus a minus b quantity squared is equal to this. Okay. So I think big piece, if you have a question like this over in the other section, take a look at the fact that you're squaring something. So this large shape that I just highlighted in orange has side lengths that are a plus b in length. So a plus b quantity squared, right? And then if you think about a minus b would be that whole length. Take away that short piece. A minus b is going to be this square that's just right here in the middle. So if you took the big orange square and you subtracted, which covered everything, right? And you subtracted that green portion, what you end up with is these 4 blue portions. And you can kind of see there's one of them here, 2, 3, and 4. And you notice each one of those is a rectangle of size a times b. So we get this really nicely with the rectangles to demonstrate why these properties of algebra actually work. Now let's see, we've got factoring. What do we have here? Simplify. Oh, using those properties of exponents. Okay, so if you have the same base, make sure, remember, we're adding those exponents together because it would just be repeated multiplication. I think probably most students get stuck on something like part D. But if I were you, I'd use the commutative property to put the 10 to the 5th at the very end first, because you don't have the same powers with the 10, the 2, and the 5, and you don't have the same base. So find things that have either the same power or the same base. And there's a 5 to the 7 and a 2 to the 7. Bring those together. And then, because 2 to the 7 times 5 to the 7 becomes 10 to the 7, this problem becomes a whole lot easier. All right. Let's see here. Here's 22 times 13 in base blocks demonstrated in a model. Let's see here. Use a similar base 5 model. Yeah, if you're doing a problem like this with base 5, just remember instead of 10 by 10, your pieces are 5 by 5. Okay, so you have ones, then you'll have little strips that are 5, then you'll have 5 times 5, which would be 25 shapes. Okay, we've got some lattice multiplication going on here. I guess I'll do one of these. Oh, shoot, maybe I'll do one of these and I'll do one of the other base just to kind of demonstrate if you need a little review of that. Okay, so let's go over here. We're going to do a little lattice work. Okay, so what do we have? 728 in the lattice multiplied by 94. And these just kind of go down the sides. Then make your grid. You could also draw your grid first and then put your numbers in if you prefer that. That's fine too. And then put your lines down. I like to make my lines kind of extend out. I'd also prefer that they were straight, but that's not going to happen today, so don't worry about that. All right, 8 times 4 would be 32, so I'll put that in a different color. 8 times 4 would be 32, so I just write 32. 9 times 8 is 72. 9 times 2 is 18. 7 times 9 is 63. 4 times 2 is 8, and 7 times 4 is 28. And then go down each kind of slanted diagonal, which forms your place values. So your ones become twos here. 8 plus 2 is 10, 13. So I bring a 1 to regroup. 8 plus 8 is 16, plus another 8 is 24. So 4 with a 2 regroup. That's a big one. 2, 4, 5, 6, 7, 8. There's an 8 and a 6. So my final answer here would be 68,432 using this lattice algorithm. Okay. Kind of a cool one. I'm not gonna lie, it's kind of a cool one. The issue is, one, it does take more drawing out, and it takes more intentionality on your part to see the place values. Okay. Let's see here. Use lattice to compute. Yeah, there's different number bases. So there we go. Okie dokie 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 dokie. All right. So if I was using what even base 5 right now. So base 5. I guess. I mean, why not? Can we do this in base 6? Just to mix it up. They seem to do so much in base 5. Let's do it in base 6. We'll be in 5-ania before you know it. So let's do this. I'm going to do 3, 2, 3. So I'm going to do base 6. So 3, 2, 3, base 6. And over here, I'm going to do 4, 2, base 6. Okay, so just remember, I am regrouping in sixes. Okay, I extend these down, I extend this down. So in my mind, I'm constantly trying to make groups of 6, just like in base 10, I was trying to make groups of 10. Okay, so 3 times 2 is 6. That's a 1, 0. 3 times 4 is 12. That's 2 6s and nothing left over. 2 times 4 is 8, which would be a 6 and 2 left over. 6, 7, 8. 2 times 2 is 4, so it doesn't have any regroupings. 3 times 2 is 6, so that's a 1, 0. And 3 times 4, once again, is 2, 0. Bring down the diagonal. 0, 5. 2 plus 2 is 4. 1 plus 1 is 2, and 2. So 3, 2, 3, base 6 multiplied by 4, 2, base 6 is 2, 2, 4, 5, 0, base, or 4, 5, 0. Yeah, 4, 5, 0, base 6. And there's my final answer. All right. I get to use a little bit of reasoning. Write these out. You're trying to find least values A and B such that the 3 groups of whatever base this is plus 2 1s is equal to 2 groups of whatever this is plus 3 1s. And there might be multiple solutions here. As you solve this, you might not be able to solve for one variable. So that's okay. You could solve for one variable in terms of the other variable using your algebra techniques. Let's see here, gives reasons for this step. So your properties, expansion, distributive property, commutative if needed, regrouping, and then simplifying. Place the digits in the box to obtain the greatest product and the least product. Ooh, yeah, that's actually a really good question. So how can I make the biggest answer possible? What should be in the hundreds place? What should be in the ones place to make the biggest thing possible? Again, keep that in mind as you do it. Let's see here. Computing which of the following have the same answer. Ooh, see, now these are really good problems because it's the goal of saying, can I rewrite the problem and get the same answer? So let's take a look and I'll do maybe one or two of these. I'm not going to do them all, but just as you're thinking about problems like this one right here, if somebody gave you 22 times 32 and somebody else was like, I don't like that problem, I think I'm going to rewrite it. They write 11 times 64. Would you get the same answer? And so remember, here's something that's really nice. You have all those properties on your side. So when you see the number 22, you could write it as 11 times 2 because you know that's what it is. And then you could use the associative property to rewrite this as 2 times 32, and you end up with 11 times 64. So I would say part B definitely is going to give me the same answer. Most of the time, we do this fairly quickly, though. I've shown all the steps to show you mathematically why it works. But you're going to find out that as you try this, it's easy to say, wait a minute, let me pull a 2 out of here. That leaves me with 11. And I bring the 2 over here, so it doubles, gives me a 64. Piece of cake. Doesn't have to be a 2 even. Could be a 3, could be a 5, whatever makes your life easier to do the multiplication with. Okay. And then this is a really fun problem. I personally, I love this problem. This is one of the great ones because there are so many cool patterns in math. And so they ask you to use your calculator, in this case, 25, 35, 45, 55. Why don't I pop into Desmos real quick and just kind of see what it looks like. Desmos, let's learn together. Doop, 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 doop. Okay, so let's do, let's start small. Let's go 5 squared. Okay, I'll go 15 squared. I'll go 25 squared. I'll go 35 squared. I'll go 45 squared. Okay. And the goal is that you start kind of looking and seeing a type of pattern here, because hopefully you 55 squared. Let me zoom back a little bit here so we can see it all. Okay. So first off, as you take a look, things that I hope you're able to pick up, every single one of these ends with a 25. Okay, so if I was going to predict the next one, I'd definitely end with a 25. Now let's take a look at the other digits here. This is a 1, this is a 2, there's a 3, there's a 4, there's a 5. What do I end up with on the other side? A 1 turns into a 2. A 2 turns into a 6. A 3 turns into a 12. 4 turns into 20. All I'm doing is looking at the first digits. Remember, we already kind of believe that the last two digits are going to be 25. Okay, so as you take a look at it, then you could say, oh, wait a minute, that's interesting. So let's look at these numbers. I have the number 2, 6, 12, 20, and now 30. And if you don't see a pattern, use some of the math that we've done before. Let's go back to chapter 1. Could I break this into something? Maybe this becomes 2 times 1. 6 would be 6 times 1, but again, that's not really maybe the best, but 6 is also 3 times 2. Okay, that's interesting. 12 is 6 times 2, 12 times 1, but it's also 4 times 3. And maybe you start to see a little bit of a pattern. Okay. This is exactly one of the patterns that we had in chapter 1, 1.2. We also had the pattern 1, 3, 6, 10, and 15. And these were what we called the bowling numbers or the triangular numbers. When you multiply them, they become what are known as rectangular numbers. But the key piece is if you start looking and seeing, you can say, hey, let me break this down. Yeah, that looks like 5 times 4. This looks like 6 times 5. And what I love is each one of the factors, one of those numbers is sitting right out in front. So 55 squared, you could say that 5 multiplied by 6 gives me 30, and then I write the 25 afterwards. So that would help you to predict if you said 65 squared. Now what we're saying is, okay, we don't know the first two, but we know the last two are going to be 25. And the first one, we take this 6, we write the next digit 7, and you multiply those, and you get 4225. So if you were to come over here and check that in Desmos and say, okay, hold on, what is 65 squared? You'd get 4225. Okay. If you want to see this, the reason why for this, then go ahead and try just taking any number at all, any group of 10, right, and calling it like A. So I have A5 in place value notation. I want to square it. That's 10A plus 5. If I write it out in place value notation, I want to square it and then go ahead and square it out. You're going to end up with something that's kind of cool because you have 10A squared, 10A quantity squared, which would be 10 squared times A squared. Plus, then you're going to have a 5 times 10A plus another 5 times 10A, which is 10 groups of 10A. And then at the end, you're going to have a 25. And the reason I say it's really cool is you can actually factor out an A from this. So if I factor out an A, and I could also factor out a 10 squared because there's 100 in each of them. So I'd have 100A times, and if you look at what's left, it's A plus 1. So this is the number you started with, and this is one more than that, and I multiply by 100, which means I just move it over 2 digits to write that down. And then, yes, I add the 25 on the end, and that's why there's always a 25. So this is a really, really cool one, and if you're multiplying things that end in 5 and you're squaring them, this is a great tool. You could multiply things very quickly with this. Okay, let's keep going. Distributive property, which property? So it's talking about the properties because we need to understand what properties work and which ones do not work. This up and down system, oh my goodness, the algebra that we get to use in this class is phenomenal because it can make your life so much easier. At least in my mind, I think it's amazing. So let me demonstrate one of those briefly. And again, if you're saying, hey, Scott's been a while since I've had algebra, that's perfectly fine. Then no time like the present to brush up on those skills. Okay. So here we go. If we did 19 times 21, right? And again, in your mind, you're thinking, I got to do all those partial products. No, you don't. And the reason is because this is really 20 minus 1 times 20 plus 1, which is really cool, right? It's like, okay, just off by ones. But if you use what we know about algebra, if you distribute this, the middle terms when you multiply are going to cancel each other off. So you actually end up with 20 squared minus 1. And 20 squared is pretty quick. So I could end up doing that problem in my head almost. And for some of you, might be able to do that completely in your head, where you just say, hey, it's really the number 20, and it just went up and down a little bit, right? So to me, that's super cool. All right. And let's see here. You could also go backwards. So this one, if I had 101 squared minus 99 squared, what would that look like? Well, let me throw a little white space back on here. So then just go the other direction. Remember, it's an equation, and maybe I'm not sure because I wasn't your former teacher, but an equation is a two-way street. If I have the quantity on the left, I can rewrite it like it is on the right. If I have the quantity on the right, I could rewrite it as it is on the left. So if I had 101 squared minus 99 squared, I could rewrite that as 101 plus 99 times 101 minus 99, because I don't want to square those numbers out directly. That might be more challenging. 101 plus 99 becomes 200. Seriously. And 101 minus 99 becomes 2. So what you've done is you've rewritten the problem into something that is way easier to deal with. And you end up with 400. So I don't know about you, but that seems like a way easier way to do this problem, unless I had to go through and do each step along the way. Yeah, use your properties. Get to use this fantastic thing called algebra to help you out. What else do we have? Base blocks. Is that everything? Oh yeah, I'm in B now. I guess I jumped forward. I should have looked down at the bottom. So yeah, this is B, and so I guess I may have just done a little something there for you as part of it. Base blocks, I don't tend to do a ton of base blocks in drawing anyway, because I don't think that that's the most effective way to demonstrate things, is to draw base blocks out. If you have base blocks, physically use the base blocks. Otherwise, it's probably not the best way to do it. So we have lattices, we have different number bases. This one's in base 5. Checking the homework problems. What else do I have? 21 to 24, 26 to 28. Oh yeah, error patterns. Students come up with ways to do these problems. So basically, this is like a student did this. What do you think they did wrong? Okay. Um, yeah, and some of them you may be saying, hey, I'm not exactly sure what they did wrong. But I will tell you that oftentimes when students do things that the teacher tells them to do, like carrying, for example, it's very easy to mix that up with other things. So like in this case in part B, 6 times 4, the student might be just fine writing 24. So they put the 4 down, then they put the 2 up here. And then what do you do with the 2? Right? What do you do with the 2? Wouldn't someone maybe at some point in time have said you add that on? So if you're in the mindset that I have to add that thing on, then you might add. So instead of 6 times 3 plus the 2, you might have just been like, look, let's just do all addition because that's what the teacher said they wanted. Very common. It shows they don't understand the concept, but it doesn't show that they are lacking all skill. Okay, I think I did assign 28. Yes, and then 34 to 35. So this is one where you get to kind of put some numbers in here and try to figure out what would make the biggest product possible. Okay, and start small. That's just, if you just had if you're struggling with these type of problems, start small. assume that you have this 0, 0 times a box 0, right? Remember, the problem solving strategies solve a simpler problem. Which of these numbers could you put in here to make the biggest product, right? And yeah, if you put a 2 here and a 3 here, it's an okay sized product. But you might be better off not putting a 2 here. Maybe I should put a 6 here. 6 times 3, that's quite a bit bigger. Well, maybe not a 6. Maybe I need a 7. And maybe this is an 8. So I could think about it. And then just remember, 700 times 80 gives you the same thing as 800 times 70. So you have to be able to see in your mind that I may need to switch those back and forth in those place values, even though they give me the same product. So start a little bit smaller and then work your way. I think you'll start to see some patterns, and that's part of the goal of a question like that. All right. I think I said 34 to 35. And yeah, it's these where you kind of, hey, can I get the same product? Yeah, I think that's 34 through 36. Multiply several two-digit numbers by 99. Oh my gosh. That is also a cool pattern. So the squaring with fives is a cool pattern. But this one is also cool. So what they're saying is take a two-digit number, multiply it by 99. So take my favorite number, 23, right? 23 times 99, right? And you say, that's interesting. Okay, looks okay. Now I'll do 45 times 99, which is Michael Jordan's other number. And you say, okay, that's interesting. And you should hopefully notice this is very close to, let's say 23 is pretty close to 2300. This 45 is pretty close to 4500, but it's off just by the tiniest little bit. And if you tie in what I talked about with subtraction, I think you're going to be just fine with this. All right, that's it for now. Off you go.